local because he spent a lot of time working with some hospital people in this area. Now he's going to talk about something also about the disease modeling. Okay.
Okay, thank you, Jinfu. Oh, it's not that many people. That's nice. I mean, there are people online, so it's good. So what I want to do today is talk about some work that interestingly has been ongoing for quite some time, but finally got finalized recently. And it's an interest I've developed in particular during the pandemic, but it had been ongoing work before. So that was working a minute ago. Wait, I think I have to be over this for this to work. Yes. I'm a bit of a geek. Some of you will inwardly groan because every time I give a talk, I show this picture and this thing. So some of you have seen this countless times. Yes. Oh yeah, I've been showing this for a while. But I do like to emphasize that this is a problem that is not new. I'm interested in the spatial spread of diseases. And I mean, it started with, so I don't know if I can do this. Oh, yes, okay, but that is very far. Okay, no, this is a quotation by Thucydides, who is one of the first historians. And what I like there is that you see that there is a description of the arrival of the plague in Athens about 2,500 years ago. And there is a notion of spatial temporal spread there, because he says the plague started in Ethiopia, then it made its way around, and finally it came in Athens. So I always like to point out that nothing of what I'm doing is new. It's been done for a while. So I also now start to do, this is COVID type presentations. I start with a thanks. This way I'll always give thanks before, if I have to abruptly finish my talk, people will have been thanked. So this is what I was saying earlier. This has been ongoing for quite some time. This was the MSc, this was motivated, let's say, by the MSc thesis of a student of mine who worked on a discrete time version of the model that I'm going to show you. But in practice, this is work that I have been carrying out with Evan Milliken, who's in Louisville. Yes, I've been there and I've been taught how to say Louisville. So he's in Louisville. And we've been working on this for quite some time. The funding, this is partly related to COVID, so this is work that's been supported by PHAC at some point. This is a paper that actually should come out soon. So what I want to do is go quickly over the problem of heterogeneity in the spread of diseases, in the spatial temporal spread of diseases. And then I'll show you this very simple model. So I want to stress the model that I'm looking at here is as simple as they come, but yet, even with its simplicity, you'll see that there is a richness, not necessarily in behavior, but in what we can find in there. So it's going to be a model for one location or two locations. So those of you who have seen me talk about metapopulations before know that I hate it when people consider only two locations. But nonetheless, this is what I'm going to do. And yet, two locations is already complex. So the first thing I want to describe is a little bit of what motivated, well, I mean, originally this was motivated by other things, but COVID really highlighted some of those problems that we were thinking of with Jason when we started the work about 6 or 7 years ago. And it's the fact that when you think about the way a disease spreads in space and time, this is not homogeneous. And I'm going to sort of explain what I mean. So, but altogether, this is all tied down to this thing that I've been doing for quite some time now, which is mobility and how mobility influences the way diseases move. And I really like to stress, okay, this has given up. This is interesting. So there's multiple modalities when you're thinking about how people move around. And all these modalities participate to the spread of diseases. And when you start to work on the modeling of people movement, you realize that it's pretty difficult because there are so many movements happening of different natures that combine to, because people that are moving are potentially hosts to diseases, so these movements combine to make disease mobile. And so it's pretty difficult to apprehend the scale at which movement happens, but it's important because it does drive disease spread. And so there's some very nice examples of the Black Death. This is working. The Black Death, for instance, in Europe, but you can see a nicely organized traveling wave in that case, because at the time movement was different. But then, for example, SARS-CoV-2, supposed to be SARS-CoV-1, of course, spread from Hong Kong through the Global Air Transportation Network. We did some work actually with one of the groups that Jinfu was mentioning that I worked with before, where we showed, for instance, that influenza A in 2009 was also conducted, the spread was conducted by the Global Air Transportation Network. Now, let's go back, actually forward to SARS and COVID-19. So this is just an illustration of how quickly COVID-19 and SARS, so SARS being the red one and COVID-19 being the blue one, how quickly they spread through space. And that is in terms of the countries and territories that were reporting confirmed cases through time. So from the day of onset of global spread, so that was in February 22nd of February 2003 for SARS-CoV-1 and 22 January 2020 for SARS-CoV-2. And so you can see that the spread at the beginning, that's how fast new countries, new territories are conquered by the disease. And so you can see at the beginning it works essentially the same way, and then there is a big divergence in terms of the behavior, where SARS-CoV-2 invaded a lot of places. But what I want to stress is that when you're looking at countries, things look remarkable like this. But when you start to dig into the details, then there is way more heterogeneity than this shows. So what I'm going to show you is the activation of health regions. The way I'm doing this is I'm looking at cases reported in a health region or in a county in the US or municipio in Mexico. And I am considering the occurrence of new cases in a 3-week period. So if there's no new case over 3 weeks, I'm saying there's not a case. And the jurisdiction lowers, so the number of active jurisdictions goes down. Okay, so what you see here is, so Canada has 122 health regions, Mexico has 2,500 municipios, and the US has 3,000 something counties. And so, for example, if you take Canada, this is the percentage of the health regions, so 122 health regions, that were active at a given instant in time. Okay? So you can see that Canada, for example, very quickly during the original spread, there was about 70% of the health regions that were reporting cases at any point during a 3-week period. But then that number decreased. So that means two things. That can mean two things. Either the number decreased because there were silent transmission chains happening. So for 3 weeks, we were not seeing any new transmission, but because we were not diagnosing them or noticing them, or the transmission chains effectively ceased and there was no transmission in the jurisdiction in question. Okay, so it's difficult to tell which it was, but it's quite striking. And Mexico is the same. You can see that Mexico takes quite some time to get to a higher level, but goes through the same. So these correspond to the waves, okay, the different waves of infection. But what's quite striking is you can see that there's, like at that point, there's 70% of municipalities that are reporting cases in a 3-week period, and then here it falls to about 50%. And when those things go back up, that's really what's interesting to me during COVID, is those resurgences, because, okay, there were no cases happening in these places for 3 weeks, and then cases started happening again. Okay? So this is a problem of importation. So what are the disparities? So as I pointed out, there's jurisdictions that had cases throughout. By the way, I should go back. You can see that the states, on the other hand, very quickly, well, not very quickly, but reached almost 100% of jurisdictions, like of the 3,200 something counties reporting cases over 3-week periods. And that remained that high throughout the, so this is to the end of 2021. And the cases remained high in those jurisdictions. But in Canada and in Mexico, we're seeing this sort of, it's not oscillatory behavior, it's simply that some of those jurisdictions are not active at some point. So, as I said, there's two possibilities to explain this. So we had silent transmission, okay, asymptomatic cases, and we know that this happened a lot, but it could also be that over a 3-week period, there was no transmission. And if you think about it in terms of the spatial spread, what's important here is there is a phase at which when you import a case, so importing a case means that someone gets to your jurisdiction while bearing the disease. But are they transmitting? Okay, so that's the second part of the equation, so to speak. It's the establishment of a disease. You import a case, that case does or does not lead to subsequent cases. And that's a very sort of stochastic process. So a variety of the works I did, we sort of summarized spread in the following way. So if you think about the spatial spread, it's the combination of, well, it's the repetition of 4 different types of events. There's a transport event during which someone travels from one place to a new place while infected with a disease. There's a potential importation. So importation, as I said, the way I think about an importation is if you come into a location and you are bearing the disease, you are an import. Whether you're a successful import or not depends on those conditions that we're going to look at. And then afterwards, a place, a jurisdiction might become an amplifier of the disease, after which it can start exporting. And that's the combination of the repetition of such processes that has led to the spatial temporal spread of COVID in this case. And let me show you some examples. So I'm going to focus here really on the beginning. So that little nudge at the beginning when I was saying, well, sometimes it works and sometimes it doesn't work. And that's really what's interesting to me. So I've taken a few examples. So they'll be somewhat random, some of them. We plotted the data for all of those jurisdictions that I was saying and went through like idiots, looking for some that looked nice. So there is no rhyme, no reason. No, some of them we've chosen for a reason, but most of the time, what I'm showing you makes no sense except that it looked nice. So that's very close to, that's very close to New York City. And so what you have is what typically happened in a lot of places. This is the number of days since the first reported case. And this is the incidence, so the number of new cases per unit time, per day in this case. And you can see that very quickly, plof, we go into something like this. Then there is a period during which not much happens. There are some cases, but not too much, and then a second wave. Jefferson County is where Louisville is, so that's where Evan is located, and Jefferson County works a bit the same. You can see that it takes a little while to pick up, and then they went through like 800 cases a day, so that's a large incidence. Winnipeg starts to look a little different. So if you look at Winnipeg, we had at the beginning when we imported the first time, we got a little outbreak, but then we petered out like this, and then there were 2 outbreaks. Yep. Oh yeah, no. So I don't care. I mean, in the sense that, okay, I'll get to that. Yes, yeah. No, of course. I'm looking at the observed data as a means to look at what's happening. But of course, when you're thinking about what's happening on the ground, it depends on what intervention measures are in place and so on. So we did some work, but this is not what I'm considering here. I have some work where we looked at the probability of importation as a function of the measures that are in place and things like quarantine and etc. But this, okay, this is just to illustrate here, okay? And yes, this is one of those randomly chosen places, Campbell County, Wyoming. It looked good. There's about 40,000 people there. Which apparently makes it the 3rd most populated county in Wyoming. But this is there, so you can see this. And this is what's interesting to me. And I'll show you another way to look at it. This is those bar graphs that we've all seen. And this is what happened prior to that outbreak that we see here in the middle. Okay, so this is the buildup to that outbreak. And what's important here is you can see these cases arriving. And I mean, coming back to the question before, okay, I'm not considering what's happening on the ground there. I'm just considering these observed cases as a representation of what is potentially happening. And you can see that this phase here, about to essentially here, cases are popping up, and then nothing is happening, and then cases are popping up and nothing is happening. So this is what we call the stochastic phase of the epidemic, where once you start to get about here, it's clear that the rate at which cases are appearing is becoming faster and faster, and you are going to go into an exponential growth phase. But prior to that, there is this phase. So what makes this phase happen? I mean, and that's the thing, these cases that we are seeing there, they're coming in because of movement. Probably, but if we completely isolated this place, I keep on hitting the wrong button. If we isolated this place at this point, you can see that transmission is really not very frequent. If there was no input into that jurisdiction, then probably the cases would just die out. Okay? And that's what we want to consider here. And when you're looking at what happens, typically it's because there is an importation of a case. So here I'm showing you influenza, because it happens not only in COVID. So this is where I come from originally, somewhere down here. They have very nice data for influenza in France. That's 2018, 2019, so prior to COVID. So the data that I'm showing here, the envelope is just the envelope of a different data for different regions. And this in red is this region here. So when you look at what happens, there is some petering phase like this, and then there's this outbreak. Now, if I look at the two regions, so Nouvelle-Aquitaine and Occitanie, so the neighboring region, and you can see these are the incidences here. And let me zoom in. And that's the thing that we tried to capture here. The idea was, okay, so how, like, you can see here, there's no incidence in Nouvelle-Aquitaine, and then there's some incidence here happening, and then the incidence kicks off, and there's this bounce back and forth between two locations where it's likely that some of the cases are coming from the neighboring region. Okay? So the idea was to try to model this. So the first one is, well, how do you model that stochastic phase? And can we show if mobility has an effect on this stochastic phase? So the model in one spatial location, I'm almost embarrassed to show it. It's so nice, simple. It's an SIS model. And we took an SIS without birth and death. Okay, so really as simple as you can make them. We're looking at a continuous time Markov chain. And so typically there's a Markov chain with only infection and recovery. So you can have these transitions. So losing a susceptible, which means that you're getting an infection, and that happens at the rate beta Si, and recovery happens at the rate gamma I, and this results in losing one infectious. But we make one very tiny little twist. So if you've done continuous time Markov chains or discrete time Markov chains for that matter, you know that typically, I mean, like in a disease model, you'll have an absorbing state. What we do is we add another absorbing state. So I equals 0 is an absorbing state. It's a natural absorbing state for that type of chain, because once you have no more infection, you can have no. I see why people were struggling this morning. Okay, I understand you. So once you have no more infection, you can have no more infected, you don't have no more infection, okay? So 0 is an absorbing state. Once you're there, you stay there. But what we do is we add an upper absorbing state, okay? We put an I hat. This thing is appealing because it's very big, but I want the pointy thing. So you put an I hat, which is such that if the number of infected reaches that level, you say, well, my process it's not terminated, but I've gone into this phase that I was looking at before, whether it's here or elsewhere. I've gone from this to this. So what I do is I put a threshold somewhere, and I'm going to explain how we choose it. I put a threshold somewhere, but it's the distinction between a stochastic phase and a quasi-deterministic phase where the epidemic is just exploding. So there's a second absorbing state in that case. And first of all, it allows, so originally I had my student, Jason, was working on a discrete time Markov chain, which has all these nice little measures you can do in terms of times to absorption and so on. There are some similar measures in continuous time Markov chains. They're not quite as easy, but the fact that we have two absorbing states does make the thing nice. So instead of just having first passage times, for example, you have absorption measures. And now the question becomes, how long is my chain going to linger in this interstate before it gets absorbed? And that is how long the stochastic phase is going to last. So here I'm showing you some examples. I've taken a arbitrary, I'm not showing units here. I've taken an arbitrary threshold there, and I've run some simulations. So the ones that are in blue have been absorbed at 0, at the disease-free, within that time period that I'm looking at, 60 days here. The ones that are in brown have been absorbed at the upper threshold, and the ones that are in red, they're the ones that are still ongoing. So you know that a continuous time Markov chain or Markov chain of any type, when there is an absorbing state, the probability of ending there is 1. Okay, so you'll always end up in the absorbing state. The question here is, how long do we spend before being either absorbed at this upper threshold or at the disease-free? Okay, and that looking at these trajectories is going to help us do this. So of course, as I was saying, there's a probability 1 of being absorbed. So if I let my time window move to the right, there's going to be more and more of those trajectories that are going to either end up at the disease-free or at the upper absorption threshold. Okay, but what we want to do is look at this. Now, there's first problem. What should I hat be? If you take it too small, your stochastic phase is very short because you end up absorbed at 0 or at the top very quickly. If you take it too large, you're essentially only considering absorption at the DFE. Okay. Now, how do you choose it? Well, there's a formula of Whittle, another one of the great ancients, that I'll show you in a second. But what we did is we used a multi-type branching process approximation, which I'll show you briefly at the end, if time permits. So the Whittle formula, it's worth taking a look because this is one of those, I mean, in the stochastic epidemics literature, it's a well-known formula. So Whittle wrote this model here, which is the probability, so that P of Si of T is the probability that there is still S uninfected and I infectious not removed in the process at this time. And there's a rate of removal of infectious and a rate of new infections in the time interval T and T plus delta T. And so what he does is he gets this differential equation for the PSI and then gets a recurrence formula to compute. And what he gets is that there's an epidemic when R0 is greater than 1. That formula only works for R0 greater than 1. There's an epidemic when R0 is greater than 1 with this probability here. So one way you can use this to solve the problem I was saying before in terms of a threshold is, well, you'll know the I0, you'll know your R0, you'll know your R0, you give yourself a probability, a desired probability of observing an outbreak, and that I0 can be your threshold. Okay, that's intuitively the first thing you can do. I'll come back to the other way to do it in a second. I just want to show you the type of thing we observe. That's for a single location. Okay? So for a single location, this graph shows you several things. It shows you the envelope of all the trajectories that we observe in terms of the mean time until, well, the mean time in the stochastic phase. Okay, so the black curve that you see here is the mean duration before absorption. I should, and that's as a function of, you see, R0. The red curve is the mean time. So this is the mean time until you get absorbed at the top, and the green curve is the mean time until you get absorbed at the disease-free. And what you can observe is that both of those guys, so the mean time to extinction peaks at R0 equals 1, which makes a lot of sense. If you're thinking you have a stochastic process, it's trying to determine where it's going. If you're at R0 equals 1, it doesn't know where it's going. Okay, it can go both ways. It's not attracted, well, I mean, it's not strongly attracted to the disease-free because R0 is not smaller than 1. It's not strongly attracted to going up. So that's where things go. But on the other hand, the mean duration itself is a bit shifted to the right, and that's quite interesting. So that means the stochastic phase is actually longer if your R0 is a little larger than 1 than otherwise. And the mean time to an epidemic, so if you're too small as R0, there's no epidemic. You don't get absorbed at the top threshold. And otherwise, the peak is at R0 equals 1, and then it goes down. Okay? Now, we took this and we wanted to look at the effect of movement, and so we added 2 locations. Again, very simple model. I'm almost ashamed. I've spent, as I said, years trying to convince people that 2 patches was not sufficient. But we did 2 because already that is complicated. So it's a simple metapopulation model, same model as before, except that we have a rate of movement between the patches. The threshold, on top of that, we take simplicity. If you think about the problem, we could have a threshold for the number of infectious in A, one for the number of infectious in B. We just take a common threshold. So when the sum of the number of infectious in both locations gets equal to I hat, we stop. And one thing is, instead of considering the 2 movement rates, we set a movement rate, that's our rate of movement, and we also set the proportion of the population that's in the A patch. And then we see this sort of thing. So here, for example, I'm taking the setup we always use in this case is we take introductions in the A patch. Okay, so we always introduce infectious individuals in the A patch, and then we look at how things vary depending on the quality of the B patch in terms of R0, and also how the population is shared between the 2. So when K is 0, 1, that means 10% of the total population is in A. When K is 0.9, 90% is in A. So it's large or small. And what you can see is that this is the duration, the mean duration of the stochastic phase. And as R0A increases, so that's where you introduce the disease at the beginning, the duration of a stochastic phase decreases with these sort of, this is the movement rate, okay? And this is when, instead of having most of the population in B, B being the patch with a very high R0, we put most of the population in A, then you can see that things are a little more nuanced because B is bad. Okay? B is the bad patch where all the infection is taking place, and we are keeping people in A. So in a way, the fact that they can stay in A where they are somewhat protected from the disease helps in terms of the duration. Sorry. We studied, I'm not going to spend a long time detailing this. We studied a variety of scenarios. I just want to get to this, just to explain briefly how we picked things, because that was, this was Evan's doing. So what he did is he derived a branching process approximation to the continuous time Markov chain. And the idea is that you can compute the probability that you end up absorbed at 0 in this case, and compare it. So I should skip on. So if you see, so the thing is, if you're absorbed at the top, so I hat being the top, then you expect that you'll end up in the, because remember, this is an I should have pointed out, this is an endemic model, okay? It has an endemic equilibrium. So we consider that we stop the model somewhere before it reaches that endemic equilibrium, okay? And, okay, so I should, so then you compute the probability of what's called a minor epidemic and a major epidemic. And what you can do is then compare what the branching process approximation does with, when you compare it to the stochastic simulations of a continuous time Markov chain. I should show you this. So essentially what we do is we approximate this probability of a minor epidemic using the branching process. Then we run 100,000 simulations in this case to compute the probability of absorption, the frequency of absorption in 0. and we raise the value of I hat until we reach a certain precision. So let me just show you. So this, what we've done, what I'm showing you here is as a function of the threshold and the movement rate, what is the error between the probability we derive from a multi-type branching process and the continuous time Markov chain. The smaller that error, the more agreement there is between the stochastic process described by the continuous time Markov chain and the approximation we get from the multi-type branching process, and therefore the stronger the agreement between things. And so essentially, and I should get to the point, we cut things out, and we did that for a variety of settings and a variety of different parameters. And we found that essentially if you cut things here, you get a pretty good agreement between your multi-type branching process and your continuous time Markov chain, which tells us that essentially picking a threshold, it's 35 in this case, the threshold of 35 does a good job of not discriminating for solutions that we would like to keep, essentially. Okay. I should point out, this was like, we submitted this paper, got some reviews, and did an insane amount of numerics. So that's about 800 million simulations. Each one of those figures I showed you is an enormous amount of simulations, because the error, essentially, you have, like, Evan was asking me to do 1 million simulations at each point. I managed to get by with only 100,000, but he did some computations which showed that, like, somewhere there was the sweet spot. So we did 100,000 because it was already getting bad. But I mean, there's a lot of numerics in there. And I think I'll skip there because this is essentially, well, maybe, okay. Let me just get to this one. Because, okay, I asked the question, so can we say if movement changes things? Yes, it does. Not so much. It was very funny because the previous version, where we were looking at the discrete time Markov chain, we couldn't see any effect at all, or barely any effect at all. Here we see a little bit of an effect, but what's interesting is that this thing is really complicated. So we've really made it as simple as we could. We've got a SIS model, we've got 2 movement rates, and we don't even have really 2 movement rates. And despite this, we have non-monotone behavior. You know, when you're looking at these heat maps, it's not just nicely organized. What seems to be the case is when you increase the movement rate, the duration of the stochastic phase decreases, which sort of jives with what we were observing before, but we're not even able to provide a sort of strong conclusion in that sense, because, for example, if you start increasing the proportion of individuals who are in the patch of introduction, then increasing the movement rate increases the reverse movement rate. Hence, we do not do 2 patches. Because that wouldn't happen with a system with more 2 patches, but that does increase the reverse movement rate, and so what you end up is mean duration that increases with increasing movement rates. So no strong conclusion, but it was an interesting thing, and I think it was something that altogether the problem of introductions of what makes a place be favorable to the introduction of a disease compared to one that is not favorable. Why does the disease go and peter out in some places and not in other places, even if they have similar on-site methods or prevention methods? I think that's quite an interesting thing, and that's just a first attempt at trying to understand this. And that's it. Sorry. I should point out this is the first time I talk about